repute like Advanced Functional Materials, JACS, Chemcom, JMCA, etc. And he was granted one patent. Okay, so sir, a very welcome. We welcome you heartily, and you can begin your session now. Sir,
Amrish sir,
Amrish, sir,
sir, I think you are mute. So please unmute yourself, sir.
I think his audio is not.
Amrish sir, am I audible?
I think there is a problem with his audio. Uh, all the participants are requested to wait for a bit.
Amrish sir, phone করতে ইয়ে করছে না। Please join.
We are currently in contact with Ambarish sir. Please wait.
Yes, Sumanaka, please wait. Please wait. Participants
Yes,
are requested to please wait for some time.
please wait. Yes, we are trying to connect with Ambarish sir.
Amrish sir, Amrish sir, am I audible to you?
All the participants are requested to wait and have patience, please, because we are currently trying to reconnect with Ambarish sir. Please wait, and we are very sorry for such inconvenience.
Omori sir, am I audible? Omori sir, am I audible? Participant, please wait for some times.
Sir, I think his audio is not connected. Ambarish sir, you can also respond to us in the chat box if you can hear us. The participants are requested to wait for some time. We are very sorry for the inconvenience. There is a problem that is being solved now. Please wait.
Amori sir, am I audible?
Hello. Hello. Hello.
Yes, sir, you are audible.
Yes, sir.
Oh,
Yes, sir. Yes, sir. Please continue.
okay. Hello.
Yes, sir.
Yes, sir, you're audible. Your screen is visible as well.
Okay. Okay. Just maybe I'll just make it full. Can you just see it full screen? I'm so sorry. I think somehow incidentally this one of my PCs crashed today morning, and there has been some problem. So can you hear and see the screen also?
Yes, sir.
Yes, sir.
No problem, sir. Sir, please continue from your end.
Yes.
So you have already started, is it? I was also waiting from 10. So
Sir, you can begin your session now.
okay. Thank you. Thank you, Dr. Moawadash and team Gkcem. I think last 2 days we had an amazing talks from right from Professor N.R. Bantopadhyay. I think to other session speakers also. So incidentally, I was told to give talk related to this workshop, this advanced materials and its characterization. So I chose a topic although it's reading as from the world of small to smart materials, and I'm trying to give you a perspective how how do we move, you have heard people talking about different materials, and just once again, I don't know what is the problem going on. So if you see, I belong to the business development group, and later on at the back end you will you will understand why I am now involved in this strategy. So I'll start off with a saying that research is the transformation of money into knowledge, whereas innovation is the transformation of knowledge into money. So with this, I'll give you a figurative sketch over the next 35 to 40 minutes or maybe more, the basics, little bit about the history of the nanoparticles, the nanomaterials development, how it evolved over the years, and whether whether it is been it's completely new, or what are the synthetic strategies and the preliminaries. Then what are the different types of preparation and preparation and methodologies, what we can do in our lab, and how we can improve on that, and the various characterization techniques. Then little bit I'll move on to the semiconductor nanomaterials, the quantum, the nanorods, the nanowires, and quantum dots. And definitely and last but not the least, I'll try to move into the next gen materials, the futuristic materials, and into how we can synthesize, convert these materials into materials which are of high end application. So with this I'll just I think most of you by this time you are very much aware what are the nanomaterials. And if you go by the conventional definition, it's materials having a characteristic length which is less than 100 nanometer. It can be a particle, the particle diameter, the grain size, the layer thickness, the length of the wire, if it's a nano wire. So precisely it is the size where our quantum size effect prevails. And and all these properties of the materials changes drastically when the size goes down to the nanometer, as you all know. You have different optical properties, the electronic properties, the conductive properties, and and so forth. And due to these different properties which are very much different from the bulk, we utilize these separate properties into different types of applications. So a person who who is giving a idea from the basics of nanomaterials to high end properties will definitely would like to you have go to the take you to the time travel where this idea already existed. Yeah, you have already heard, I think, day before yesterday, but still I would like to tell you that the famous Lycurgus cup, which you all know. It was a you see, it's a image of King Lycurgus, but what has happened, it puzzled a lot of people. It was not solved until some 1950s, where it was scrutinized. The glass material was scrutinized, and it was seen that the broken fragments, it was unintentional completely, that the artisans who actually made this, they actually impregnated glass with particles, small particles of silver and gold, as low as 50 nanometers. So what happened is that, if you view this cup from the rear end, that is, if you see the transmitted, the blue end of the spectrum gets transmitted, and eventually what you see is a red color. Whereas if you see the cup in the from the front end, that is the reflected, right, you see it's green color. So this is still there in the probably the British Museum. And this is this gave the idea that this golden, this color, there's a drastic color difference, how you actually see. Then how, then if you travel to the medieval Europe side, if you see this is the structure which which you might have already seen also in some places, that is the structure of the glass pane of, I think, Notre Dame Church. So it's a specific structure where it was believed that the alchemists produced this red and yellow colors by mixing gold chloride and silver nitrate in the molten glass. So this method of reduction of these metallic salts is very, very close to what we actually do even today also. So this is in the era of, say, medieval Europe, some 500 BC and AD. So so it was actually known. Then I have not shown yet, then we have some that no, it's also shown that the Deruta ceramicist, who actually made this beautiful saucers and cup plates. So it was also seen that specific during the preparation, ultimately they did it by without knowing it, but ultimately they got that idea, that trend, and they eventually doped this small particles of gold, silver, as well as copper into this uh, iridescent, this ceramics. And basically in this ceramics you get this color. So who has been the game changers? Like, why I'm taking you a little bit very specifically, like, how we moved in from the age old time, and what we are doing is just like, not very different, but the thing is that we have now better systems, better methodologies to analyze. So some of the key developments during the, like, nowadays in the modern era, and I think that goes back to again 1857 in the, like, present domain, where I think Michael Faraday, like, discovered this colloidal ruby gold. So everybody, like, most of the people didn't know that, gold was also ruby red in color, and it could also change to different, colors, also pink, and it can be, like, the color can be tuned by different, by tuning the different sizes. So what he did, like, part of this process, he involved the washing of the gold, where actually Faraday noticed that, this color. So he actually kept the samples in different bottles and used them for, like, several experiments, shining a beam of light. So what he observed a cone, what he observed a cone was very, very, like, well defined in the fluid, and which was produced by the illuminated particles. Okay, this was probably known as the Faraday-Tyndall effect, and because of this discovery, like, he's also known as, as the key researchers, or, like, key discoverers in nanoscience and nanotechnology. Then comes, we give a, drastic change, where I highlighted this 1947, where one like, like person called John Bardeen, who actually discovered this semiconductor transistor, and he expanded the scientific knowledge into semiconductor interfaces. Then the first, in the year 1958, we got Kilby, where, like, who originated the concept on, designed and built the first, like, IC, which actually received the Nobel Prize very recently, like in 2000. So apart from this, if you then move to the next era, that is the 1950s to the 2000, I think everybody of you who, again, who, well, like, who is talking about this thing, will definitely talk about the Feynman's talk, Richard Feynman's talk, and, like, the, the famous quote that, there's plenty of room at the bottom. So what did he actually mean by it? What did he actually mean by it? He actually asked that question that, can we write the entire 24 volumes of our Britannica on the head of a pin? Like, at that time, like, at that era, he just gave a thought to this. So if you see, if you see, the head of a pin is actually 1/16th of an inch. So if you magnify it by, some 25,000 times, 25,000 diameters, it will actually be the entire area the Britannica covers. Okay, so basically what you are doing, you are actually reducing the size. So if you basically reduce the size of the entire Britannica by 25,000 times, you can actually write it. So that's the basic idea behind how, like, things of miniaturization, like, the idea came into, like, foreground. So, but however, like, even when the idea came in 1959, after 15 years, in 1974, the first term, nanotechnology was coined by, I think, Japanese scientist called Taniguchi. So that was the initial time, and he actually gave a definition known as, it consists of proper processing of separation, consolidation, deformation of materials by one atom or one molecule. And then the series came. We have the series of, invention of the different types of instrumental techniques, and the atomic force microscopy, and the different institutes were actually founded. And there was a policy also development, where, like, the working group, even in our country, working group has been formed, and nanotechnology initiative has been generated. So this is my last slide on where, like, on where, like, where about the history. You are actually, like, I've already told about, in the left hand side, you are seeing, like, how from the medieval period, this idea of development of, like, of nanoparticles and nanomaterials generated. And on the right hand side, you can see, like, what are the different years when these instrumental techniques came into being. And we, like, it's all about the interaction of the material with electromagnetic radiation that we are actually utilizing in all of these, like, instrumental techniques. So I would just like to highlight this, the right hand side. In 1981, this one Russian scientist called Akimov discovered this semiconducting quantum dots in a glass matrix. and that conducted pioneering studies in different electronic and optical properties. 1985, Bruce discovered this semiconductor nanocrystals. Similarly, as you all know, the carbon nanotubes were also discovered by Sumio Iijima during the year 1991 and Bhavanthi. So apparently, why I why I wrote these 3-4 names, because incidentally three of them won the Nobel Prize this year. And so definitely it's not the work which was done very recently, but so it has been done quite a long time ago, right from say 15-20 years back. So how do you classify these nanomaterials? You can classify, this slide doesn't show you the exact picture. This is a kind of only it shows a particular picture. So you can definitely classify on the basis of its origin, in the sense that you have natural nanomaterials where it can be formed in different forms in nature, including your protein molecules, then clay minerals like clay, then natural colloids, in milk and even in blood, and so on, the spider silk and so on. Then you have the artificial nanomaterials where it comprises of semiconductor materials, quantum dots, the carbon nanotubes, and so on, and different metal based also nanoparticles. Then you have you can classify these nanomaterials into what I'll say on the different structural configuration of the composition. So in that you have the organic nanomaterials where it can be all liposomes, the micelles, the reverse micelles, and so on, the biodegradable nanoparticles and so on. Then we have the inorganic nanomaterials, which we are doing, the metal based nanoparticles, metal oxide. I think metal oxide uh, uh, examples of such are which are very frequently used is silica, titania, zinc oxide, and even aluminum oxide. And these have remarkable properties if you compare with their metallic analogs. Then finally we have the semiconductor nanomaterials. Then I left out this carbon-based nanomaterials where we have graphene. I think graphene is also one of the most highly studied materials, which is actually a hexagonal network of honeycomb lattices made up of carbon atoms on just 2D planar structure. So what does this, different types of infer? It can be, so a nanomaterial can be what I'll say, differentialized into form of a zero-dimensional nanostructure, where you have all the 3 dimensions within the narrow range, say within 100 nanometers. And what are the examples? The quantum dots, the fullerenes, those are the examples. In case of 1D nanomaterials, in this class, they have uh, have 2 of the 3 dimensions in the nano regime. That is one of the dimensions. It's outside the nanoscale. Okay, so this is a fantastic graph in the right, on the right hand side. You can see which classifies actually what are the 3 types and what are the examples of those 1D materials. Those are say nanofibers, nanotubes, nanorods, even and so forth, nanowires. We have then the 2-dimensional nanomaterials where we have the plate-like shapes, where the two dimensions are outside the nanometer regime, but 1 dimension in the nanoscale. And what are the examples? You can have this graphene, you can have these thin films, multi-layers, the nanosheets, then even the fibers. Those are the 2-dimensional. What are the 3-dimensional? You have all the bulk materials are, they are not necessarily confined in the nano regime, in any regime. So all of this, they can be at free dispersion in a solvent and so forth. Okay, so how do you actually then synthesize, synthesize in the sense the synthetic methodologies, and basically what happens, you are actually in the altering the density of states. I have not gone into the, I've not in technical things where density of states, where you can have different as a stepwise stepwise, or or a discrete single line, where you can for as different from a 2D or a 1D or a 0D nanostructure. So Coming to the synthetic methodologies, you all know that there's a top-down approach, and top-down approach where it's actually a destructive method which decomposes several bulk materials into smaller materials, and which then actually transform into nanomaterials. So there are different techniques. You have the ball milling technique, then you have the lithography technique, laser ablation. So basically, what you do is, in supposing lithography, it's actually a process of printing a required shape or structure on a light sensitive material. Okay, so on a mask actually. So basically these are the there are some inherent disadvantages in this top down approach. One disadvantage is that the requirement for a very complex equipment, and the associated costs are also very high. But the advantage is in the fact that they can go for a bulk industrial production. Okay. Then you have a laser ablation technique where you generate the nanoparticles by striking a target material with a powerful laser beam. Okay, so these metal atoms, they vaporize, and immediately they are solvated by the surfactant molecules to form nanoparticles in the solution. Then you have a sputtering method, uh, thermal decomposition, which is caused by heat. The process is endothermic. The chemical bonds are broken, and it's divided into the smaller by heat, by thermal energy. So it's broken down at a particular temperature to form the nanoparticles, which are subsequently produced in chemical reaction. Then you have a arc discharge method also. Fullerenes, then the carbon nanotubes. These are generally used, prepared from those methodologies. Like coming to the bottom up approach, which is actually the more used approach in which we use. You can have sol gel method, where actually a suitable chemical solution, it serves as a precursor. Metal oxides or chlorides, they are common, preparation of those, they are mainly used in this sol gel procedure. Then you have a spinning method, where you actually spin coat the material and you actually develop it. Then you have a CVD method. Then you have different template type of method, soft and hard templates method, the laser pyrolysis. The template method, it's a very conventional method for this generation of nanostructures. You have several block copolymers, then flexible organic molecules, anionic, cationic, and different surfactants through which you can generate the nanoparticles. Then we have different reverse micelle methods. Reverse micelle methods they are also used, but they are actually very handy for making different sizes and shapes also. Like water in oil emulsion, you'll have all the hydrophilic uh, heads inside, you're pointing towards the water in a core. So definitely you can have a nano material which can be which can be aqueous, or soluble in water solvent. Then you have a different biological or a biosynthetic method, which I think it's not written here, but definitely several microorganisms, fungi, even bacteria, they are used for the synthesis of nanomaterials. uh, Different metals, in that sense. Then even from the biosynthetic methods using biological templates, and even different plants, plant extracts, they contain these proteins which actually are able to uh, uh, actually reduce and make these nanoparticles. No, now that a very detailed idea you might have already be having. So I'll move into the different characterization techniques which you are aware. You have if you do the structural characterization for a bulk structure, you have a ACM, you have a transmission microscope. For the surface structure, you have an STM, or a surface topography, you have an ACM. Whereas in case of surface composition, I think XPS is a very, very strong tool, and which I prefer personally very much. And the analysis of it, you can do lots of analysis through that for characterization. So now that I've been told to little bit what I'll say, concentrate on the semiconductor, quantum dots. This is an amazing system, semiconductor quantum dots, where different types of materials can be synthesized, and what happens in these materials feature amazing optical and electronic properties, and which can be engineered through different composition and the crystal structure. So it all depends how you actually synthesize them, how you assemble them, and uh, then that renders them applicable for different applications. So, and further, this semi quantum dots, they actually are additional lever. How, their size is reduced to a nanometer scale in the 3 dimensions. So you have a restricted electron motion, which actually leads to a discrete atom like electronic structure and size dependent energy levels. So this enables the design of nano materials with widely tunable light absorption. You have a bright emission of pure colors, and you have a control over the electronic transport, and even you can widely tune the chemical and the physical functions, and because of its very large surface to volume ratio. Now what happens, in this what we talk about this quantum dot, basically you do a quantum confinement where actually the electrons are constant to a domain which is compared to the de Broglie wavelength. Okay, so again they can be classified into separate different areas. So this actually slide we actually shows you what are the different types of applications which you can get from synthesizing as well as assembling different these type of quantum dots. You can do a bioimaging where these quantum dots can be actually targeted, obviously there has to be a ligand exchange, proper ligand, and they can be targeted to an antibody, and they can be imaged on so as a biomarker. Then you have the size dependent absorption and emission, and obviously the what people have been doing for the last so many years is the photovoltaic cells. They have been concentrating, obviously the efficiency has not been that much, but still nevertheless people are working. So I think this is that image which actually shows uh, that you have a when you have a discrete atom like density of states in that figure A, whereas as the quantum dots become smaller, this quantum confinement actually increases, which actually increases effectively increases the effective band gap and leading to a blue shift. So you can actually play with the band gap, and since you have a quantum confinement, so basically you can induce several defects it's into the system, and you can play around with the band gap, and that is how different applications are generated. So the graph shows a very discrete energy states. I'll not go into the very details of it, but these are the types of things which you can see. Okay, then in that in the right hand side you can see that this is some techniques where um, these quantum dots have been synthesized, the at the initial long back in 1981, I think. So in molten glass, some this semiconductor materials were actually dispersed, and you actually through heat treatment, then you actually got this. So this is age old method. Then you have a molecular beam epitaxial method, where epitaxial, where you can actually synthesize this gallium arsenide or indium gallium arsenide, these kind of materials. And then then the I'll then you have the thin film technique. So basically what is happening that this band gap of these quantum dots, they can be tuned across different ranges, right from, and it falls in the visible region, right from UV to IR. Okay. So, and the last one, last one is the very chemical synthesis, which actually is used by many people, where it's known as a one pot synthesis, where typical homogeneous growth of this quantum dots are observed. So but generally I'll just show this one, how what is done. You have a shrink line, and you have several surfactants, like generally this triactyl phosphine oxide is used, and the precursor is used like dimethyl cadmium. And basically you actually heat this in a to suppose 100, and these reactions generally occur at around 100 to 300 degrees centigrade. And then this is arrested, arrested by quenching. And essentially it all depends how you actually set the reaction parameters, and eventually you get different types of quantum dots, then this nanorods and even tetrapods. And similarly, then you can assemble them, assemble them through different types of techniques, through say a drop casting technique, where you can have as say you can drop casting technique that is not very controlled approach. You can have an electric field assisted, where the area becomes also high. You have a self-directed, HOPG on a HOPG, graphite lead, you can actually synthesize. And then you have a electrophoretic deposition also, through by applying electric voltage. Hello, hello, hello.
Yes, sir. Sir, it is audible, sir.
Okay, so okay, no problem. I just thought that some recording stopped, so that's why. Okay, so these are some of the structures which actually were synthesized in the labs. And you have the cadmium selenide, then the cadmium sulfide, and various types of nanorods. So eventually, they have been assembled over large areas, So this is basically have been synthesized in the organic sol or in the organic medium. Whereas the bottom picture shows that they have been transferred into the aqueous medium also, and there has been phase transfer by use of different pluronic surfactants and block copolymers, and this ensemble of these nanorods have been generated. So these are kind of different synthetic strategies. Then I would just like to highlight some of the different applications where this is used. The quantum dimension, quantum dot materials, I think they are used for these displays and lightning. So if you see in displays, the red, green and blue colors are mixed to obtain the entire color palette. Okay, so this is known as a chromaticity diagram, where actually they used to quantify and the quality of the color which is actually used in our regular LED TVs. Okay, so if you so you can see from the the bottom graph, in quantum dot LEDs, the intensity is very intense, as if you even compare to the organic LEDs. So this actually, for the quantum dots with actually twofold electron hole band-aid states, is the with this, I think with this you can also use this in lasing applications. I'll skip this for the two slides. So basically another application where actually I'll come to this slide, where this kind of nano rod synthesis which I actually showed, they are used very specifically in our for solar energy harvesting. It is used in photovoltaics. So basically what you need to do, I have shown you that assembly picture. So you can actually tune the different the diameters of the different nanorods. You can have a bimodal distribution. And play with the synthetic strategies, and eventually generate high efficiency this solar cells. So basically in this recent years, these quantum dot solar cells, they have seen a rapid increase in this performance, which even reaching to I think 14-15 percent. So basically these solar cells could benefit from different multiple exciton generation, in which two or more of the electron hole pairs are generated upon absorption of a photon, which is actually in which the energy is greater than the band gap. Okay, so this is one of the key applications. This also I have shown. And then the last application where I will focus on is the sensor part. Today's sensors, as the available gas sensors are mainly based on nanostructured metal oxides. Okay, these sensors, these are kind of our strength areas where these sensors exploit actually the large surface to volume ratio and the high reactivity of the semiconductor material to create chemiresistors, whose actually the electrical resistance is dependent on the target gas concentration. So through this development of this quantum dots, you can actually generate a device where you can actually sense different types of gases, like say a nitrogen dioxide gas or a methane gas, and they have enormous benefits in terms of application. So this is this figure shows actually where we developed a quantum dot in octane and then we did a drop casting, and then we did a ligand exchange, and and then we actually dried it out and taken the powder, and we have measured the sensing performance, the sensing response to NO2 actually. And by developing 2 layers, 4 layers, we can actually uh, increase the sensitivity as well as the sensitivity of the sample. Now, this actually covers the entire gamut of more or less the gamut of application in which our semiconductor materials are synthesized and used for various applications. So the next slide is something different which I like to highlight. At the end of the day, so forth, till now I think whatever I have shown, that is good for our publication. We can publish, we can synthesize the material, do a specific characterization XYZ and so on, and whatever the changes, whatever are the observations we can highlight. But from a perspective, I just like to highlight this point, because now what we are moving, ultimately at the end of the day, even after publishing a paper, you would like to have a something a material which can actually convert into a device. Okay, so convert into a device, and definitely you are not the only one who can actually make the device. You need basically a synergistic effort from various departments or divisions and so on. So the what we are trying to do, we are actually synthesizing this material, and for this for this I'll just like to highlight this. Why? Because we are talking about now, whenever we are writing a proposal or so and so, even to to any agency, whether it's a DST, DBT, or even any other agency, people are asking about the TRLs, the technology readiness levels. So basically, where we are, that we need to know very well. Whereas mainly whatever we are doing when we are developing the material, we are at a level of TRL1 or TRL2, where this technology readiness level is actually is known as where the technology concept has been formulated, and we have an experimental proof of concept. The basic principles have been observed. Then we have then we move to a gamut, this is the major part, the region from TRL4 to TRL6. That is the technology which has to be validated. You have a proof of concept, you have developed the material, you have a proof of concept, then that needs to be validated in a relevant environment, environment, industrially relevant environment. Then there has to be a demonstration. So that is the level where TRL4 to TRL6 goes. And TRL7 is where you have that system where you have the device already generated, prototype developed, the device has been validated in the industrial environment, and the system has been qualified to perform. So now the concept of this manufacturing readiness levels has also come into play, where this is mainly looked by industries. Why I am telling these things? Because the moment when you are synthesizing this, you are synthesizing these materials. Obviously, people will ask, what is your readiness level? If you are going to an industry, if you are trying to even talk to some agency for funding or whatever. So they are given like in a scale of MRL1, and this is globally accepted. This TRL level is given by NASA, so this is globally accepted. So you need to also look on these things. So that is our role is limited. Why I told mine to market, we are already synthesizing this, we are making these materials, but to take this into the market into a full-fledged device, you actually need some effort. Then so basically what you have an research ideation, the invention, you have a prototype, and what is lacking in our part is the field trial or the pilot plant. That needs to be done, obviously, like if you connect to a stakeholder and different types of I told you it's private goods in the sense like who will be the beneficiaries of those materials. Somebody has to take those materials, like we are publishing, that's fine, absolutely, but some industries, some starters, even some small startups, there are hundreds of now startups who are actually looking for those materials to actually make this. So there are the private players. Then you obviously the big strategic players are there, where uh, different types of application are needed for either even in defense, and we are working for this strategic sector very much. Then you have a societal in the sense that you are developing a material and a membrane. You are developing a membrane where you are actually employing those materials. So those are the sectors where the say suppose your water filtration membrane and so and so the socio-economic departments. So why I told in these things because once you develop this, you need to also think along those lines. So how do we move from this now that we have developed these materials, these materials, and we move on to the smart materials. Why I told smart materials? Because these are the materials which can be manipulated to respond in a controllable and reversible way. You can modify some of their properties as a result of external stimuli. So you can through a mechanical stress or even temperature. So because of their responses, these materials are also known as responsive materials. They are also termed as active. So these materials now uh, uh, this whatever we have discussed, this semiconductor, whether it's a nano rod or a nano dot or whatever, they actually are the building blocks of this smart materials. They are now, you have heard of the smart fabrics. I have tried to give you a overall picture on how we are moving from this domain of nano to the high-end futuristic areas. You have these smart fabrics where you have a self-cleaning where super hydrophobic. So that is what which actually employs these type of materials. Then in aircrafts, then you have in concretes and different types of areas. So these are the types of spectrum of activities where actually we are looking on. The sensors are actually, we are actually preparing these chemical sensors, the electrochemical sensor, where we are trying to develop these sensors from the materials which already I have discussed into detection of say pesticides through by an electrochemical technique. Then even you might have heard that presence of bisphenol, although it's written that all our these pet bottles there's no containing BPA, but it has been seen that although it is written some of these even leach out, and we have done a study actually the leaching effect of this BPA is actually harming our next generation very very much. You never, they're silent killers. There's absolutely silent killers. You have all these ADHD syndromes and all this stuff. So basically you do a environmental monitoring through testing of pesticides and water monitoring. Then you have this moisture sensor in the sense that you can detect trace amount of moisture in say transformer oils, which are very much needed for any industry. Then you have a biomedical sensors. Then definitely you have the piezoelectric actuators where you are actually you are having these nano generators. I think Dr. Deepankar Mandal tomorrow will be speaking specifically on these things, so you can have a typical idea on this. You have this singular graphene, and you have phase change materials. I've already told this is a nano generator where it actually converts this mechanical energy into the electrical energy based on this piezoelectric material. You use a P-ZT type of material, and you actually blend with the polymer, that is a kind of PVDF, and this is used even as sensors which are used in submarines. Okay, these are sonar. Then this is also used as a. These are the works which we are trying to do in partnership with our agencies, and the next generation materials where you are always hearing that smart watches, flexible wearable electronics, where through the watches you can actually monitor your entire day-to-day function. So this is what the basis forms through these piezoelectric materials. Then this slide I would like to show where I just, these are very recent, where we are trying to develop some phase change materials through those semiconductor materials, which we actually I have discussed basically the theory of it, how different applications we are looking at. This is actually we are doing. So this is a kind of transient movement from the initial to what we have done. So these PCMs, in areas where even if you go out of Calcutta, there are scheduled power offs, 2 hours, 1 hour, even more than 2 hours. So you cannot just keep milk or even frozen meat outside the frozen temperatures even for 1 hour, 2 hour, because again if you freeze it, obviously it will get bad. So we are trying to develop a material which will actually store the latent energy, take the latent energy, and so that there is a power up, they actually will keep the system cool. So these are all TRLs mentioned. TRLs, and please don't tell TRL level, because TRL is also already technology readiness level. So 2 means that we are already having a proof of concept. We have already having a prototype developed. That is 3. We actually move to this kind of regimes. Then this is already, I have told, the frozen meat and so on. And this is the last slide where I'll show that these are the sensors where even they can be used for sensing, for structural health monitoring. You can actually we are deploy these piezo sensors across different areas of bridges, and do an online mapping that where there is been a crack, where which is being done by in Calcutta it is being done, but definitely these sensors are now imported. So definitely they have an amazing, amazing, we have a market where actually we can work on these things, and we can develop this into device ready things. So with this, I think I'll finish off, because I had and obviously there is a last one I would like to say, the electrochromic devices. Okay, electrochromic devices, like if you have traveled through any of those, say earlier it used to have the tinted windows. So in that Dreamliner kind of aircraft in Air India, so where you can actually press a switch, and obviously the your glass gets tinted. So these are the types of materials we are developing, tungsten oxide graphene nano composites, where they can be made on a made like a coating on the glass panel, and eventually by applying voltage we can actually switch it, you can have different coloration. So they have an innumerous applications, right from tinting a glass window, or even strategic applications where you need to actually camouflage and so on. So I think this is definitely the last slide. So I have tried to give you a very overall idea on what is the synthesis of the synthesis procedures, what are the typical synthetic strategies, which definitely by this time you are definitely very much aware of it. But still I went a little bit inside, and then came to the semiconductor materials, and how these materials can be fine-tuned, their band gap can be altered, and that can be harnessed for different applications. Then I gave you a glimpse of some of the futuristic materials where these kind of elements, or composites which are synthesizing, can actually move into this regime. And that's all from my side. Thank you, Dr. Muvadas and the entire team, for actually doing this workshop. They're amazing. My colleagues from CSIR, from Delhi, where I belong, and then CGCRI, the students definitely they are and CSIR for the funding. Thank you. And since this online, I hope somebody might be awake. So thank you all. Hello.
Thank you, sir.
Thank you very much, sir. Participants are requested, if you have any question, please ask, sir.
Thank you. I think you can. I think you have the email address. I think if there are any specific questions, hello. If there are any specific questions or anything, or you can like like to collaborate or anything, do you can just drop a mail and we'll see.
Amrit sir,
Yeah, I'm very much
Amrit
there.
sir, Amrit sir, am I audible?
Yes.
Yes,
I-
sir. Sir, please take it as a granted from our end, sir. This is a token of appreciation for you
Thank you so much. Thank you very much.
for this lovely presentation, sir. Thank you once again, sir.
Thank you. Thank you very much.
Thank you so
Thank
much, sir.
Thank you. Thank you. And sorry for the initial thing. I was actually there, but
No, sir.
No,
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 sir. It's okay.
no issues,
No, sir.
sir.
It's
No
okay.
issues, sir.
Sure. Thank you.
No, sir. We are very much pleased for as per your lecture. I hope the participant you have learned so many things from sir in sir whatever sir has told to you. Thank you once again, sir, for your beautiful and lovely presentation.
Thank you so
Thank
much.
you,
Thank you very much.
All the
sir.
participants are requested to fill up the feedback form that is given in the chat box.
Thank you. Can
All
I
the
just
participants
yeah.
are. Please fill up the feedback forms. And there will be a second session in the after lunch session, which is we will join strictly at 1:45 p.m. Please join on time, and thank you for being here. See you after lunch. And please do not forget to fill the feedback forms. Thank you.
Thank you, madam. Thank you all.
Thank you.
Thank you.
The assignment link is also given. Please please complete the assignment and join strictly at
Participants are requested to please fill up the assignment link as well
assignment
as
form.
feedback link from your end as soon as possible. And also you are requested to join from 1:45 p.m. We will
1:45
start
p.m.
the second session at 2 p.m. That is the next speaker will be joined within 2 p.m. So please join within 1:45 p.m. Thank you all.
Thank you, everyone.